Right, so the last important review or preliminary topic for stochastic processes is special probability distributions, okay? So in this review, we'll be looking at the special discrete probability distributions, which entails the Bernoulli distribution, linear distribution, geometric distribution, and Poisson distribution, okay? We have other types of special discrete probability distributions, but we'll just focus on this ones for now, okay? Then the second session in this review will be on special continuous probability distributions, which will include the gamma distribution, exponential distribution, and normal distribution, okay? So as I have already indicated, we have other special probability distributions, but we just want to focus on these ones because these are the ones we are likely to come across in the course of studying stochastic processes, okay? All right, so now let's begin with the first session on special discrete probability distribution, beginning with the Bernoulli distribution. All right, so now before we give a formal definition for Bernoulli distribution, let's take a look at the following. A Bernoulli trial is any single trial of an experiment that has two mutually exclusive outcomes, okay? So yeah, the mutually exclusive outcome basically means that if we have an observation or individual belonging to one group or category or outcome, you can't have the same observation or individual belonging to the other group or category or outcome, okay? So this means that we can have only an observation belonging to one group or category at a time. For example, yes or no in an election, okay? When there's an election, is either you vote for party A, which is for yes, or party B, which is for no. You can't vote for the two parties at the same time, okay? So we are going to have an individual or observation belonging to one of these parties at a time. Also, head or tail in a toss of a coin, okay? For example, when there's a football match, we have two teams and one team will go for one of these outcomes, either head or tail. We can't have a team picking the two outcomes at the same time, okay? We say that one team go for head and another team will go for tail, okay? Also, dead or alive as a person comes out of a surgery. After every surgery, is either you are being classified as a dead person or a person who is alive, okay? And also male or female in childbirth, okay? When there's a childbirth, it's either you are being classified as a male group or a female group, okay? So these are some examples. Now, a sequence of Bernoulli trials will form a Bernoulli process, okay? For example, if we want to observe the outcome of childbirth in a hospital on a daily basis, then this is going to be a Bernoulli process, okay? Because on the first day, we are going to observe an outcome of either a male or female group. On the second day, we're also going to observe an outcome of either a male or female group. So this is going to be sequential. So because we are going to observe a Bernoulli trial on a sequence of some time domain, this will be a Bernoulli process, okay? Now let's take a look at the definition for Bernoulli distribution. A discrete random variable x is said to have the Bernoulli distribution with parameter p if its PMF is given by equation 1. So in equation 1, this p is a parameter of interest, which is basically the probability of outcome of interest, okay? Because for Bernoulli trial, we have two mutually exclusive outcomes, either yes or no, or good or bad. We often classify the outcome of interest as success and the outcome that is not of interest to us as failure, okay? So the probability for that outcome of interest is a p, okay? And the probability for the outcome that is not of interest to us is 1 minus p, okay? So the random variable x can only pick value 0 or 1. 0 means that the outcome of interest cannot occur, and 1 means that the outcome of interest will occur, okay? Now let's take a look at some conditions regarding the Bernoulli distribution. 1, each trial of an experiment results in an outcome that may be classified as a success or failure, okay? So for Bernoulli trial, we have two mutually exclusive outcomes, either yes or no, or good or bad, okay? So the outcome that is of interest to us, we often use the term success for it, and the outcome that is not of interest to us, we often classify it to be failure, okay? The second condition states that the probability of success P remains constant from trial to trial, and the probability of failure denoted by Q, which is equal to 1 minus P, also remains the same, okay? So let's take an example. If you have to toss a fair coin, we know that the probability of observing either a head or a tail is going to be what? 1 out of 2. So the probability for our success, let's take, for example, we are interested in head. So the P is going to be the probability of head, and which is going to be 1 out of 2, okay? And Q is going to be the probability of the tail, which is going to be also 1 out of 2. And these probabilities will not change anytime you have to perform the experiment over and over again, okay? So if you have to perform the experiment for the second time, the probability that you are going to observe a head will still be 1 out of 2. And the probability that you're going to observe a tail will also be 1 out of 2. So if you have to perform this experiment 1,000 times, these probabilities will still be the same. It will never change, okay? And the third condition states that the trials are independent, that is, the outcome of any particular trial is not affected by the outcome of any other trial, okay? For example, if you are to toss a fair coin and in our first trial we are to observe a head, it does not necessarily mean that in our second trial we are going to observe a tail, no. So the trial that we are going to, sorry, the outcome that we are going to observe in our subsequent trials has no influence on the outcome that you have already observed in our first trial or the current trial, okay? And also, the random variable x is a binary which assumes the values 0 and 1, okay? So 0 means that the outcome of interest will not occur, and 1 means that the outcome of interest will occur, right? Now let's take a look at some properties of Bernoulli distribution. So suppose x has the Bernoulli distribution with parameter p, then the expectation of this random variable x is going to be p, and this is similar to the mean of the random variable. Also, the variance x, the variance of our random variable, which is var of x, is going to be p q, okay? And also the moment generating function can also be defined in this form, okay? So remember that q is equal to 1 minus p, okay? Right, so now let's take a look at some example. Suppose that a fair die is tossed. Let y be a binary such that if one occurs, such that if 3 occurs, we record it as 1, and if any other number occurs, we record it as 0, okay? So we want to find the distribution of y and use it to find the standard deviation of the random variable y, okay? So let's take a look at this solution. So when a die is tossed, a 3 occurs or a 3 does not occur. So we have binary here. When a 3 occurs, it is recorded as 1. And any other number that occurs, which is not 3, we record it as 0. So we have a binary outcome here. Now, if the die is fair, the probability of a 3 occurring is going to be what? P, which is called 1 out of 6. So the probability of the outcome of interest, which is P 1 out of 6, okay? Since the outcomes from different trials are going to be independent, Y has the Bernoulli distribution with probability mass function defined below, okay? So 1 out of 6 is the probability of a 3 occurring, and this 5 out of 6 is the probability that a 3 will not occur, okay? So the random variable Y here, 0 means that a 3 will not occur, and 1 means that a 3 will occur. Now we want to find the standard deviation of the random variable Y. So first, let's get the mean. You know that the mean is expectation of y, which is equal to p, and our p is 1 out of 6. And the variance is going to be pq, right? Our p is 1 out of 6, and our q is 5 out of 6, okay? So this will give us 5 out of 36 once we take the product of this. So therefore, the standard deviation is going to be the square root of the variance, which will be in this form, okay? So this will bring us to the end of this first session. All right, so I hope you join me in the second session on binomial distribution.